Hello everyone, I welcome you all in 30th lecture of the course Process Equipment Design, and here we are going to discuss design of reboilers. Okay, and this is the last lecture of 6th week also. So, in this particular lecture we will start design of vertical thermosiphon reboiler. So, let us focus on the steps one by one. The first step is we have to define the heat duty, or we have to compute the heat duty. And how we can compute this? Because I already know that how much vapor I need to generate. Okay. So, that vapor flow rate into lambda will give me the heat duty, and this is the simple calculation. So, once I am having the heat duty, what we can consider next? If you remember the last class, if you remember the last lecture, we have discussed maximum possible heat flux available in vertical thermosiphon reboiler, and its value was around 37, and its value comes as 37,900. Okay. So, we will start with maximum allowable heat flux, so that this heat flux should never be exceed during the design. Okay. Because whole design will depend on this value only. So, once you know the heat duty, once you know the heat flux, you can find out heat transfer area of reboiler, right. So, in this way area you can calculate without considering U factor, okay, because here I am having another factor which is more important, and once that factor will be maintained, we can compute heat transfer coefficient. Okay. So, in second step you can find heat transfer area, okay, and after that we have to decide tube dimension, that is the diameter of the tube and length of the tube, and we will calculate the number of tubes required. Okay. So, in vertical thermosiphon reboiler we consider only one pass, one shell pass and one tube pass, right. So, whatever number of tubes you obtain, just consider next value to this, because number of tubes should never be in decimal. Okay. So, whether it is even or odd, it is immaterial, because we provide only one pass in tube side. Okay. And after that we have to assume very important parameter, and that is recirculation ratio. Okay. And to start this calculation we should consider recirculation ratio as 3:1. Okay. Now, what is this recirculation ratio? Okay. This is basically the ratio of liquid and vapor available when it is returning back to the distillation column, right. Let us say if I am maintaining 3:1 recirculation ratio. So, in this 1 is vapor and 3 is for liquid. Okay. So, let us say 4 kg per second feed is entering from distillation column bottom to reboiler. So, in which 1 kg per second vapor will be there and 3 kg per second liquid will be there when the mixture of vapor and liquid exits reboiler and enters to the distillation column. Okay. So, here we are assuming this ratio, fine, and through the calculation we will try to maintain this recirculation ratio. Once this recirculation ratio will be maintained, then only we will proceed for heat transfer coefficient calculations, right. Now, once I am having the recirculation ratio, I can find out vapor flow rate which is leaving the reboiler, because whatever vapor flow is there in the reboiler, that you have to calculate, and that you know a priori that how much vapor is to be generated. So, now you have vapor flow rate as vapor flow rate as well as recirculation ratio. So, considering this, you can find out liquid flow rate which is leaving the reboiler, and addition of liquid flow rate plus vapor flow rate will give the total feed to the reboiler, right. So, in that way you can find out vapor rate, liquid flow rate as well as the feed rate to the reboiler. Now, once you have that recirculation ratio and vapor and liquid flow rate, you have to maintain two phase pressure drop throughout the tube. Okay. And And as we have discussed in kettle reboiler design, that the pressure drop generate in the reboiler because of two phenomena. First is due to friction and second is due to static head. Okay. Here friction generated due to vapor, we are not considering that, as we have considered in kettle reboiler, because here mixture moves, not the vapor only, right. So, first of all we will focus on pressure drop in the tube due to friction. Okay. So, let us see the empirical correlation for that. So, here I am having the empirical correlation for pressure drop due to friction, where I should find out JF value and L dash, this is basically the total length, and UT is basically tubes, and UT is basically tube side velocity. Okay. And M value will depend on the flow, that is either laminar or turbulent. So, you can choose M value accordingly. Now, the point is how you should consider this. Okay. We can consider this at two different points, at the entry point and at the exit point. Why? Because when the fluid is entering into the reboiler, it is pure liquid, right, and when it is exiting the reboiler, it is a mixture of vapor and liquid. So, when I am computing the pressure drop, I should calculate mass flow rate per unit area, fine, that we represent as capital G. Okay. So, that is same when feed is entering and when the mixture is leaving the reboiler. Okay. But where we will find the change? We will find the change considering UT parameter, that is the velocity in tube side, because when it is entering, the feed is pure liquid and density of the liquid should be considered. However, when it is exiting, we should consider density of the mixture, not the liquid or not the vapor, right. In this way we can find change in velocity, and so we can find the Reynolds number, and we can see JF factor, and we can find out pressure drop. So, this pressure drop due to friction you have to calculate at entry level and at exit level. Okay. So, this pressure drop due to friction you have to find out at entry and exit of the tubes, and you should consider average of these two value as pressure drop due to friction in tube side, right. And secondly, we should consider pressure drop due to static head, because liquid will always available in tube side. Okay. And why we have considered the friction? Because that liquid vapor mixture moves throughout the length. Okay. So, as far as static head is concerned, we have the expression like rho GL, fine, but here we are considering this differently, because I am having different condition of feed at inlet as well as at exit condition. So, here we should consider a specific volume instead of densities. Okay. So, you see here I am having a specific volume at outlet, and here I am having a specific volume at inlet, and this is nothing but meter cube per kg. Okay. So, that is just reverse of the densities, and here I am having ln V naught by Vi, because this specific heat is, because this specific volume of the feed is continuously changing from inlet to outlet. Therefore, we have considered ln value of this ratio, right. But if you consider this particular expression, this is nothing but rho g h, fine. So, total pressure drop in tube side will be what? That is due to friction, which we have seen in the last slide, and that is due to static head. Addition of these two will give total pressure. Addition of these two will give total pressure drop in tube side. So, that pressure drop we should compare with the pressure drop which is available, right. So, to understand that, we should consider vertical thermosiphon reboiler. Like this, and here I am having the distillation column. This is the liquid level, and it is returning back from this side. Now, what will happen? If I consider the inlet pipe, okay, and upper tube sheet will be equal to at the level of the same level where liquid is available in distillation column. So, this distance is nothing but the length of tube. Okay. Now, what we have computed? We have computed pressure drop in this tube, right, and this pressure drop which is available in this tube should be compared with the pressure drop available here, and that is nothing but rho g L, right. So, what will happen? Whatever pressure drop is available over here, it should be larger in value in comparison to pressure drop in this tube, then only it will be able to push this liquid upward and circulation can be maintained. I hope it is clear to you. So, now we have to find out available head, and available head where? In the distillation column. Fine. So, if I know the length of the tube, I can simply find out pressure drop in, we can simply find out pressure drop in distillation column side, and that will be rho L G H, and that will be rho L G L, right. So, now we compare total estimated pressure drop and the available head. If available head is greater by a sufficient amount to allow for the pressure drop through the inlet and outlet piping, we accept the design and proceed further. If not, we have to return to second step and increase the number of tubes. Okay. So, how I should increase the number of tube? In second step, we have considered maximum heat flux. Fine. Now, we will reduce heat flux from the maximum value. Okay. And after reducing the heat flux, when we will calculate the area, area becomes larger than that is available with maximum flux, right. So, if we fix the dimension of the tube, we can find increased number of tubes, okay, and whatever feed is entering into the tube previously, now it is entering to more number of tubes. So, it will reduce the velocity and so the frictional loss. Okay. However, if you want to change available head, you cannot do anything because density of the fluid is constant, G is constant and length is also constant. Whatever you can change is only the frictional head, okay, and that can be affected by number of tubes. Okay. So, in this way, first of all you have to maintain the recirculation ratio, and then we should proceed for the calculation of heat transfer coefficient. Okay. So, as far as heat transfer coefficient is concerned, we find that through Chen's method. Okay. So, here I am having this vertical thermosiphon reboiler, and I am having different points here like B, C and D. Okay. So, what will happen at point B? At point B, fluid is below its boiling point due to static head effects and thus undergoes sensible heating. Okay. So, usually fluid enters to reboiler at boiling point, but because of some losses over here, it may reach below boiling point. So, first of all sensible heat should be supplied, and if I am providing the sensible heat, we should consider convective heat transfer, right. So, further at point C, what will happen? Fluid will reach to its boiling point, and after that vapor formation will start. Okay. Further, if I consider the flow pattern between C and D, here boiling will takes place. Okay. So, heating takes place by both nucleate boiling and two-phase convective mechanism. Heat flux supplied through tube walls causes partial vaporization and rapid acceleration of the flowing two-phase convective mechanism. So, as far as boiling is concerned, we should consider nucleate boiling as well as convective boiling, but that will occur at upper section, okay, or when we consider at the exit of the reboiler. At entry of the reboiler, pure convective heat transfer will be there. And further, at point T, two-phase mixture will be available which exits it and returns to the column for disengagement of vapor liquid. Okay. So, in this way we can understand the heat transfer mechanism in vertical thermosiphon reboiler. So, let us start the calculation of heat transfer coefficient using Chen's method. So, effective heat transfer coefficient should be what? effective heat transfer coefficient at exit of the tube should be equal to HFC dash and HNB dash. Okay. So, HNB dash nucleate boiling coefficient you can find either by this equation or by this equation, and here you see this is HNB, we have to consider HNB prime. Okay. So, how this prime will be considered, that we will see. Okay. So, let us start the calculation of heat transfer coefficient. Okay. So, first of all we will focus on nucleate boiling coefficient. So, that can be calculated considering the correlations for nucleate pool boiling which we have just seen in the last slide, and that should be modified by a factor Fs, and this Fs basically accounts for the fact that nucleate boiling is more difficult in flowing liquid. Okay. Because when we consider the nucleate boiling, we understand that the fluid is at a stagnant position, but here fluid is continuously moving. So, whatever coefficient we obtain for nucleate boiling, that should be reduced by factor Fs, right. So, maximum value of Fs should be 1. And here we have this graph to find out Fs, which is basically suppression factor, and it can be obtained corresponding to REL FC power 1.25 as you can see on x axis, right. So, first of all we will consider what is REL. So, REL basically 1 minus x GdE by mu L. Okay. Now, what is this REL? Because we have already considered recirculation ratio, right. So, whatever feed is entering to the reboiler, whole will not remain in liquid position when the mixture exits the reboiler. Okay. So, let us say if I am having 3:1 ratio, so 1 minus x value should be 0.75. right, and G is the mass flow rate per unit area which will be fixed at inlet and outlet both conditions. So, in this way you can find out Reynolds number for liquid only at exit position. So, once you have REL, we can find FC value in next slide, and so you can see Fs value from this graph. So, HNB dash is basically equal to HNB into Fs, right. And next is we have to and further we have to consider convective coefficient, okay, because when liquid is available and vapor is available, we have both mechanism of heat transfer, convective heat transfer as well as nucleate pool boil as well as nucleate boiling, right. So, convective coefficient, that is HFC, is calculated assuming that liquid phase is flowing in tube alone. Okay. So, here we have the correlation for convective heat transfer which we also consider in shell and tube heat exchanger, right. And however, in vertical thermosiphon reboiler, fluid is continuously moving. Okay. So, whatever Reynolds number we obtain as REL, the same Reynolds number will be applicable over here because this HFC is purely corresponding to liquid, right. So, convective boiling coefficient HFC dash can be estimated using equation for single phase convection heat transfer, and that should be corrected by factor FC, okay, to account for the effect of two phase flow. Okay. So, HFC dash should be equal to HFC into FC. So, FC you can obtain from this graph where on x axis 1 by x Tt is there. So, the value of 1 by x Tt you can find from this where you are considering x as well as 1 minus x. So, this is basically vapor quality and this is for liquid, and similarly we have liquid and vapor properties, right. So, 1 by x Tt basically counts two phase flow, okay, and considering Fc and HFC we can find out corrected convective heat transfer coefficient, okay. And once you have the value of Fc from the last slide, you can also find out value of Fs. So, the effective heat transfer coefficient when the mixture is exiting the reboiler should be equal to HFC dash plus HNB dash. Okay. So, that heat transfer coefficient is available at the exit. Okay. Now, what will happen when the fluid is entering into the reboiler? Fine. In that case, the complete feed is available in liquid form, okay, and there only convective heat transfer will take place. So, we will use this expression as it is with the change that this Reynolds number corresponding to complete feed, not 1 minus x, right, as we have considered in HFC dash. Okay. So, this Reynolds number will change and you can find out HFC value at the inlet of the reboiler. So, the final heat transfer coefficient in tube side. So, the final heat transfer coefficient in tube side should be average of HCB as well as HFC. Okay. So, in this way you have to find out heat transfer coefficient in tube side. Okay. And shell side heat transfer coefficient you can find because steam will be available, or if any other vapor will be available, you can simply consider condensation process and find out heat transfer coefficient in that side. Once you have these two values, you can find out overall heat transfer coefficient and compare that with the estimated. Okay. So, you calculated, you have already found from this thermosiphon reboiler calculation, and you required or you estimated, you can find out from the system because you already know the heat flux. Okay. Until unless you will not fix Q value, you cannot proceed further. Okay. So, Q value you already know and that should be divided by delta T mean. Okay. So, it will give me U value and this U value you can consider here. Okay. So, whatever U you have calculated, it should be more than U required. Okay. However, when I am considering more overall heat transfer coefficient, my area should be less, right. However, if I consider U required lesser than U calculated, it means I am already having sufficient heat transfer area. So, this condition should be satisfied. I hope you understand the procedure to design vertical thermosiphon reboiler. Okay. So, that is all about vertical thermosiphon reboiler. Now, we will see forced circulation reboilers, but I am not going into detailed design of this. Okay. So, as you know that forced circulation reboiler includes pump, and that we can consider, and in that we can consider boiling either in tube side or shell side. Okay, because we are using the pump, and few more points we will discuss about forced circulation reboiler, that it includes STEMA E shell, and these units are characterized by high tube velocity because I am using the pump in order to mitigate the fouling. So, scale formation can be reduced by increasing the velocity, and that can be done with the help of pump. Okay. Now, if you think that why we need forced circulation, when the fluid is not able to circulate on its own, and when it will happen, when I am dealing with highly viscous liquid, right. So, forced circulation reboiler should be used when viscosity of the fluid increased, when viscosity of the fluid increases then 25 centipoise. Okay. Otherwise, we should use other reboilers. Okay. Because forced circulation reboiler, when you are using the pump, which gives extra cost. Okay. So, for each purpose, such type of reboiler utilization becomes uneconomical. Okay. So, that you have to keep in mind. Now, in this slide we will see the selection of reboilers, and if you see I am having different process conditions and reboiler type. So, we are comparing kettle or internal, and here I am having horizontal shell side thermosiphon reboiler, we are having vertical tube side thermosiphon reboiler and forced flow reboilers, right, and we are having different operating condition. This table extends to this section also, we are having different other properties. Okay. Now, if you consider different, now if you consider different alphabets which are shown like this, okay. If we elaborate this, B stands for best, it means the reboiler gives best performance. G is for good operation, F for fair operation, but better choice is possible. Similarly, RD is risky until unless we have not designed it carefully, okay. And capital R is risky because of insufficient data, P is poor operation, and E operable but unnecessarily expensive, right. So, depending upon all these category, we have given different alphabets to different reboilers, right. So, in this table you can find out where B is available, okay. So, if you keep on counting the B, in most of the condition you will find B in vertical tube side thermosiphon reboiler, okay. Let us see that. Here I am having B like 1, 2 and 3, 4, and here I am having no B, and here I am having B at 2 position, okay. Now, if I see next part of this table, we do not have any B in kettle reboiler, and in horizontal shell side condenser and in horizontal shell side thermosiphon reboiler also. However, we can have B 1, 2, 3 and 4, 4B over here for vertical tube side thermosiphon, and for circulation we have B like this, okay, where we are dealing with heavy fouling liquid and highly viscous liquid, right. However, if you compare these B, you will find that vertical tube side thermosiphon reboiler is most versatile and its utility is maximum as far as industrial operations are concerned, okay. So, in this way you can choose the desired reboiler depending upon the conditions, and here I am having some of the references which you can go through. And now I am having summary of the video, and this summary includes the summary of the complete topic, that is design of reboiler, which we have considered in lecture 27, 28, 29 and this lecture, that is 30th lecture. So, summary of these videos are here. Reboiler and its applications are discussed, type of reboilers are detailed with its working, difference in operation and design of kettle, thermosiphon and forced circulation reboilers is discussed, heat transfer fundamentals of reboilers are described. Further, design steps of kettle and vertical thermosiphon reboilers are discussed in detail. Finally, we have seen how to select the desired reboiler depending upon the condition, okay. So, that is all about design of reboilers, and I am stopping this lecture over here. So, thank you everyone.